Imagine a universe where cosmic forces far beyond our control lurk in the shadows, quietly threatening life as we know it. Black holes that devour entire stars, magnetars that can shred spacecraft with their magnetic fields, and blazars hurling plasma jets directly at us. These are not just figments of science fiction, but terrifying realities. And yet, amidst these mind-boggling phenomena, there remains a deafening silence. Despite the vastness of space, we have yet to hear a single whisper from intelligent life. This overarching theme of cosmic horror, where the universe seems more hostile than hospitable, begs a chilling question. What's out there, and why haven't we heard from it yet? We're forced to confront the fragile place of life within the universe through the lens of these unsettling cosmic phenomena. From ghost galaxies to the mysteries of the Great Attractor, join me as we explore them. Galactic filament collapse. The universe's bones could disintegrate. The universe is an intricate web of structures with galactic filaments acting as its colossal bones, holding together galaxies and clusters in a delicate balance. These filaments are the largest known structures in the universe, stretching across hundreds of millions of light years. They form the framework of the cosmic web, connecting galaxies through thin, thread-like strands of dark matter and gas. Imagine them as the spine of the universe, where galaxies form like beads on a string, with the spaces in between, vast cosmic voids, serving as the gaps. But these structures are far from permanent, and recent studies suggest that the filaments holding the universe together could eventually disintegrate. Galactic filaments rely heavily on dark matter to maintain their structure. Dark matter is the invisible force that accounts for most of the universe's mass, exerting gravitational pull that keeps galaxies and filaments in place. Without dark matter, the gravity holding these massive structures together would not be enough to prevent them from falling apart. But dark matter's behavior is still a mystery, and any shift in its influence could have disastrous consequences for the cosmic web. It's as though the scaffolding holding up the universe could be eroded, leaving galaxies to drift apart, untethered. The potential collapse of these filaments is not just a theoretical exercise. It could have real consequences for galaxies themselves. If the filaments disintegrate, the connection between galaxy clusters would break down. Galaxies would become isolated, and the flow of matter, gas, dust, and stars that moves along these filaments would halt. Star formation in galaxies along these filaments could slow dramatically. These galaxies rely on the inflow of gas from the filaments to fuel the creation of new stars. Without this constant supply, star formation could dwindle, and galaxies could eventually fade away. The cosmic web is not just a passive structure, it's an active participant in the formation of galaxies. Within the dense cores of filaments, galaxies form and evolve, constantly drawing in material from their surroundings. But the idea that these filaments could collapse is linked to the expansion of the universe itself. The universe is expanding, and this expansion is accelerating due to dark energy. As space stretches, the filaments too are stretched thinner. If the forces holding them together, like the gravitational pull of dark matter, are not strong enough to counteract this expansion, the filaments could break apart, leaving galaxy clusters isolated in the void. There is also the question of how filament collapse would affect galaxy mergers. Galaxies are constantly interacting and merging with one another, particularly in the denser regions of the cosmic web. But if the filaments collapse, the mergers that help shape galaxies could slow down. Galaxies would no longer have the gravitational scaffolding to guide them towards one another, reducing the frequency of these cosmic collisions. Over time, this would lead to fewer galaxy mergers, changing the evolution of galaxies across the universe. Current cosmological simulations, such as those using the illustrious TNG project, have begun modeling the potential evolution of these filaments. These simulations provide a glimpse into how the universe's structure might change over billions of years. They show that filaments may weaken or fragment over time, particularly as dark energy accelerates the universe's expansion. The cosmic web's intricate structure could unravel, leaving behind a more chaotic universe where galaxies no longer follow predictable paths. Galactic filaments are vast and diffuse, making them difficult to study directly. They are composed of tenuous gas and dark matter, both of which are hard to detect with traditional telescopes. However, recent advances in radio and X-ray astronomy are beginning to reveal more about these elusive structures. Telescopes like the Square Kilometre Array, SKA, and the European Space Agency's Athena X-ray Observatory will be key in studying the large-scale structure of the universe and detecting any signs of filamentary collapse. Another crucial factor that could contribute to filamentary collapse is feedback from active galactic nuclei, AGN. These are the powerful energy sources at the centers of galaxies, driven by supermassive black holes. AGN can release jets of energy that heat the gas within filaments, potentially destabilizing these structures. Over time, the energy released by AGN could cause the gas within filaments to expand, reducing the gravitational forces that hold them together. In extreme cases, this could lead to the collapse of entire sections of the cosmic web. It is intriguing to think about how cosmic voids, the large empty spaces between filaments, may be affected by filament collapse. The gap between clusters of galaxies may widen when voids expand due to filament disintegration. A cosmos much more dispersed and disconnected from one another than the one we know today would be the outcome of this. Galaxies might end up as isolated islands in a vast ocean of nothingness if filament collapse causes these voids to spread to an unprecedented degree. But is this collapse already happening? Some regions of the universe show signs of filamentary weakening or fragmentation. For example, observations of certain galaxy clusters have revealed regions where the filamentary structure appears to be breaking down. While it's unclear whether these observations represent the early stages of filament collapse or other cosmic phenomena, they suggest that the large-scale structure of the universe is far from static. The collapse of filaments could have implications for other cosmic phenomena. For instance, cosmic rays, high-energy particles that travel across the universe, may rely on filaments as pathways. If these structures collapse, it could disrupt the distribution of cosmic rays, potentially reducing their flux in certain regions of space. This would have implications for our understanding of cosmic ray sources and their interactions with the universe's large-scale structure. The idea of filament collapse is related to more general concerns over the universe's ultimate destiny. The demise of these structures, according to some wild speculation, might herald the start of the end of the universe. Isolation of galaxies and a colder, darker cosmos would result from the cosmic web's unraveling. According to this theory, which is called cosmic death, the progressive burning out of stars and the ultimate disintegration of matter into space-time filaments might be the first stages leading up to the universe's heat death. Do you think this collapse is bound to happen? That's a tough question. We still don't know everything there is to know about the forces that control the big picture of the universe, especially about dark matter and dark energy. Ghost galaxies. Galaxies made almost entirely of dark matter. Stars, for many of us, symbolize life, brilliant, warm, and the very essence of energy. But there's a type of galaxy that almost defies this understanding: ghost galaxies, eerie collections of stars that exist primarily because of dark matter. These structures, which are made almost entirely of dark matter, challenge our basic perceptions of galaxies and the nature of the universe itself. Most of what we know about galaxies comes from observing the stars, gas, and dust they contain. But ghost galaxies turn this assumption on its head. Unlike their bright, glowing counterparts, these galaxies are dominated by dark matter, a mysterious substance that makes up about 85% of the universe's matter but doesn't emit light. This means that ghost galaxies are almost invisible to our telescopes, but they leave behind telltale signs. So, how do scientists even know they exist? The answer lies in the phenomenon known as gravitational lensing. When light from distant objects passes through or around these dark matter-heavy regions, it bends. This effect creates distortions in the images of far-off stars and galaxies, offering indirect proof of the existence of ghost galaxies. These gravitational distortions act like a cosmic fingerprint, revealing that something massive, but unseen, is lurking in space. But here's where it gets interesting. These galaxies aren't just faint, they are ultra-diffuse. Their star density is shockingly low, often 100 times less than what you'd find in a galaxy like the Milky Way. This creates an eerie cosmic shadow, galaxies that appear as faint smudges, barely holding on to any visible matter. While ordinary galaxies have a gravitational pull that matches the amount of visible stars and gas within them, ghost galaxies do not follow the same rules. In fact, their behavior is often counterintuitive. When astronomers observe how stars move within these galaxies, the speeds don't make sense based on the visible matter present. The stars in ghost galaxies seem to zip around much faster than they should, unless, of course, there is dark matter providing the extra gravitational pull. This creates an unsettling scenario where these stars appear to be floating through an invisible sea of dark matter. The ghostly stars only represent a small fraction of the galaxy's mass. The rest is completely unseen, creating a galactic enigma where dark matter plays puppet master, dictating the galaxy's movements and structure without us being able to directly observe it. Ghost galaxies fall under a broader category known as ultra-diffuse galaxies, UDGs. These UDGs are particularly strange because they can be as large as the Milky Way, but contain far fewer stars. One example that has captivated scientists is Dragonfly 44, an ultra-diffuse galaxy that is 99% dark matter. Imagine this: a galaxy as wide as our own, but with almost no stars. It is a skeletal version of the Milky Way, a structure where dark matter is overwhelmingly dominant, holding it together. The few stars it does contain drift through its ghostly body like wandering souls, providing just a faint glimpse of visible matter amidst the sea of darkness. Dragonfly 44 and other UDGs challenge the idea that galaxies need stars to exist. Here, dark matter does most of the work, acting as the invisible glue holding these faint objects together. But what could lead to such a lack of stars in galaxies this large? Scientists believe that intense gravitational interactions with neighboring galaxies, or even dark matter itself, could have stripped these systems of the gas needed to form stars. You'd think ghost galaxies would be isolated and distant from other galactic bodies, but surprisingly, they are often found in galaxy clusters, nestled among far brighter and more typical galaxies. For instance, the Coma cluster contains numerous UDGs, with ghostly appearances hidden within a sea of glowing galaxies. These ghost galaxies survive within these clusters, likely due to dark matter's gravitational influence. The dark matter in ghost galaxies seems to shield them from being torn apart by the gravity of nearby massive galaxies. Without dark matter, these fragile structures would not be able to maintain their form. Ghost galaxies may represent one of the most compelling pieces of evidence we have that dark matter is real and plays a fundamental role in the universe. These galaxies are living laboratories for studying how dark matter behaves on a cosmic scale. While we can't see dark matter directly, its effects are undeniable in ghost galaxies. By observing the movements of stars within ghost galaxies, scientists can map out dark matter in unprecedented detail. These galaxies allow astronomers to test theories about dark matter's nature and interaction with visible matter. Are ghost galaxies the key to understanding dark matter, or are they just another layer of mystery in the cosmos? Given that ghost galaxies have so little visible matter, it's surprising that they remain stable and don't collapse under their own gravity. What prevents these galaxies from tearing apart? One theory is that dark matter acts as a stabilizing force. While ghost galaxies lack the dense concentrations of stars seen in typical galaxies, dark matter might exert a gravitational pull that keeps everything from unraveling. In other words, Dark matter provides the structure and stability that visible matter alone cannot. Why do ghost galaxies form so few stars, despite their size? Some theories suggest that dark matter prevents gas from cooling, a critical step in star formation. Without cool gas, stars can't coalesce, leaving these galaxies with vast regions of dark, starless space. Alternatively, it's possible that early collisions or interactions with nearby galaxies stripped these ghost galaxies of their gas, leaving them unable to form stars. In either case, the end result is the same: massive, ghostly structures filled with dark matter, but nearly empty of stars. There is also a belief that some ghost galaxies could be the remnants of galactic collisions. In these cases, most of the visible matter, such as stars and gas, would have been stripped away, leaving behind a faint and dark matter-heavy shell. These skeletal remains of galaxies could linger for billions of years, their original form lost to time, but their dark matter halos continuing to exert a gravitational influence. Ghost galaxies might even outlast traditional galaxies. Because they are dominated by dark matter, which doesn't emit light or lose energy in the same way that stars do, these galaxies could persist long after their stars have burned out. In a sense, ghost galaxies might be immortal, quietly existing in the universe's vast emptiness for eons, long after more familiar galaxies have faded into oblivion. Given how difficult they are to observe, scientists suspect that there may be far more ghost galaxies than we currently realize. Could ghost galaxies vastly outnumber regular galaxies? It's possible. The faintness and diffuse nature of these galaxies mean they often go unnoticed, hidden in plain sight among the stars. If ghost galaxies are more common than we think, it could radically change our understanding of galactic evolution. Instead of being anomalies, ghost galaxies might represent a significant but largely unseen component of the universe. Cosmic ray showers, the universe's silent deadly rain. Cosmic rays, high-energy particles originating from space, bombard the Earth constantly, mostly unnoticed by humans, yet these rays hold a silent, deadly potential. Many of them come from supernova explosions, where stars collapse in a fiery end, ejecting cosmic debris throughout the universe. However, recent studies show that they might also emerge from other extreme events like black holes and active galactic nuclei, adding to their mysterious origin. The most powerful cosmic rays, those carrying unimaginable energy, travel across vast stretches of space, originating from galaxies or other unexplored cosmic regions. Cosmic rays consist of charged particles, primarily protons, helium nuclei, and other heavier elements. These particles are often accelerated to near-light speeds, making them some of the most energetic phenomena in the cosmos. Although invisible to the naked eye, their presence becomes apparent when they crash into the Earth's atmosphere. Upon impact, cosmic rays trigger a chain reaction, creating a shower of secondary particles that cascade down toward the Earth's surface. This process is referred to as a cosmic ray shower, where the once single particle becomes a rain of subatomic particles, including muons, neutrinos, and electrons, scattering in all directions. Earth's magnetic field offers some protection from these cosmic invaders. Acting like a giant shield, it deflects many of the lower energy cosmic rays, preventing them from reaching the surface. However, high-energy cosmic rays can bypass this protective field and penetrate deep into the atmosphere, causing radiation showers. Scientists have set up vast detection systems to track these particles, like the Pierre Auger Observatory in Argentina, which is one of the largest cosmic ray detectors in the world. By studying the particle showers that cosmic rays create, scientists can gain valuable insights into their origin and properties. While most people remain blissfully unaware of cosmic rays, their impact on human health, particularly for astronauts, is a subject of great concern. Space is teeming with cosmic rays, and without the protective cover of Earth's atmosphere and magnetic field, astronauts are vulnerable to high levels of radiation. Prolonged exposure to cosmic rays has been linked to an increased risk of cancer, genetic mutations, and even cognitive impairment. In fact, one of the major challenges of long-term space travel, such as a mission to Mars, is developing effective shielding to protect astronauts from these harmful rays. Even on Earth, people living at higher altitudes or frequent flyers are exposed to slightly higher levels of cosmic radiation. Beyond human health, cosmic rays pose a threat to technology as well. Satellites orbiting the Earth are regularly bombarded by these high-energy particles. Cosmic rays can damage the electronics on board, leading to malfunctions, or in some cases, the complete failure of the satellite. This makes space missions increasingly difficult, especially as humanity ventures further into space. The impact of cosmic rays isn't just limited to technology in space. Even communication systems on Earth can be affected. High-energy particles can disrupt radio signals, GPS systems, and even internet connections. A hypothesis proposed by Danish scientist Henrik Svensmark suggests that cosmic rays could affect cloud formation. According to this theory, cosmic rays help create cloud condensation nuclei, the small particles around which clouds form. More clouds could, in turn, lead to cooler global temperatures. Although this idea remains controversial, it opens up fascinating possibilities for the role of cosmic rays in shaping our planet's weather and climate. Cosmic rays are often categorized based on their energy. Galactic cosmic rays, originating from outside our solar system, are among the most energetic particles known. But even these pale in comparison to ultra-high energy cosmic rays. These particles carry more energy than any particle accelerator on Earth can produce, leaving scientists puzzled about their origin. Some of these ultra-high energy cosmic rays may come from interactions with dark matter, or even from the energy released during galaxy collisions. Despite years of research, the exact source of these particles remains one of the great unsolved mysteries of modern astrophysics. When cosmic rays strike the Earth's atmosphere, they often produce muons, which are heavier cousins of the electron. These particles can pass through hundreds of meters of rock and soil before decaying, making them valuable tools for studying the internal structures of the Earth and even ancient buildings. For example, scientists have used muons to peer inside the Great Pyramid of Giza, revealing hidden chambers that had previously been undiscovered. Some scientists believe that cosmic rays could have contributed to genetic mutations, potentially driving the process of evolution. In the distant past, supernova explosions in our galactic neighborhood may have flooded the Earth with cosmic rays, increasing mutation rates and possibly influencing the development of new species. But cosmic rays may also have a darker side. There is speculation that they could have triggered mass extinction events by increasing radiation levels on Earth, though this remains a topic of debate among researchers. The ozone layer is being gradually removed by cosmic rays as well. Ozone depletion can occur when these particles interact with atmospheric molecules, especially when the sun isn't shining brightly. Because the ozone layer shields Earth's living organisms from dangerous UV radiation, this process is quite worrisome. The most important findings in particle physics have been aided by cosmic rays, which are both mysterious and potentially dangerous. Crucial to our knowledge of the forces that bind atomic nuclei together, investigations employing cosmic rays in the early 20th century led to the finding of new subatomic particles, such the pion. Neutrinos are enigmatic particles that exert negligible interactions with matter. Researchers have just lately been able to discover them thanks to cosmic ray studies. Researchers are hoping to learn more about the universe's basic elements by examining cosmic rays. One of the strangest findings in cosmic ray research is the presence of unexplained anomalies in detection data. These anomalies suggest the existence of unknown processes or particles that defy our current understanding of physics. Some researchers believe that these anomalies could be the key to discovering new physics beyond the standard model, the theoretical framework that describes the fundamental forces and particles in the universe. Certain high-energy anomalies detected in cosmic rays may be the result of dark matter interactions. If confirmed, these findings could provide crucial evidence for the existence of dark matter, a mysterious substance that makes up about 85% of the universe's mass, but has yet to be directly observed. Planck stars, the final rebirth of black holes. In the bizarre realm of black holes, where everything seems destined for annihilation, Planck stars offer an unexpected twist. They are proposed to be the ultimate resolution to the information loss problem and could provide a cosmic rebound for black holes. When black holes collapse, the traditional narrative says they form a singularity, a point where gravity pulls matter into an infinitely dense point. But Planck stars suggest a more intriguing fate for these mysterious entities, and their very existence could rewrite everything we know about black holes and quantum gravity. Planck stars are theorized to be an incredibly dense core that forms in place of the singularity once a black hole's collapse reaches the Planck scale. The Planck scale is where space-time itself becomes granular, like grains of sand, no longer a smooth fabric as described by Einstein's theory of relativity. It's the smallest measurable unit in physics, and it is this realm where quantum effects take over. When a black hole forms, its collapse seems unstoppable. The overwhelming force of gravity should crush everything into an infinitely small point. But Planck stars introduce an alternative. The collapse would not continue infinitely, but would be stopped at the Planck scale due to the extreme density. In this state, matter is theorized to be compressed but not entirely crushed, creating the Planck star, a tiny, superdense core that stores all of the black hole's information. Why does this matter? For years, physicists have puzzled over the information paradox. Information, in the sense of quantum physics, refers to the properties of particles. The paradox arises because black holes, according to classical theories, seem to destroy this information forever once particles pass their event horizon. But quantum mechanics says that information cannot be lost. Enter Planck stars, which provide a potential answer. They would store that information in a compressed form, meaning that the information isn't destroyed but preserved, waiting to be released back into the universe eventually. The wildest aspect of this theory is the idea of a bouncing black hole. After matter collapses into a Planck star, it could potentially reverse its collapse, leading to a bounce-back event. This would slowly release the black hole's contents back into space over incredibly long periods of time. It's a mind-bending concept, considering that from our perspective, due to the extreme time dilation near the event horizon, this process could take longer than the current age of the universe. What we perceive as the slow evaporation of a black hole via Hawking radiation might actually be the early stages of this process. Speaking of Hawking radiation, it plays a key role in understanding how black holes lose mass over time. Traditional models say that black holes shrink slowly due to Hawking radiation, where particles are emitted from just outside the event horizon. But in the Planck star theory, the end stage of a black hole's life could be much more dramatic. Instead of simply fading away, the Planck star might cause a massive explosion, releasing all the trapped energy and information at once. This explosion would be unlike any supernova or gamma-ray burst we've ever observed, possibly producing high-energy particles or even gravitational waves that could be detected with future technology. This scenario of a Planck star's rebirth raises a huge question. What would such an explosion look like? The energy released from a collapsing black hole is already immense, but the idea that this could all be unleashed at once would make it one of the most extreme events in the cosmos. Detecting the remnants of such an explosion could be challenging, as it would likely be rare and brief. However, scientists are already looking for potential clues in high-energy cosmic rays and bursts of radiation that could fit the description of a Planck star rebirth event. The finite lifespan of black holes is an important point here. In classical physics, black holes were thought to be eternal, with their event horizons persisting indefinitely. But Planck stars, introduced the idea that black holes might only last for a finite period before returning their contents back to the universe. It suggests that black holes could eventually vanish entirely, changing how we see the long-term future of the cosmos. A fascinating link that arises from the Planck star theory is its potential connection to cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. Just as the universe expanded from a tiny quantum state, Planck stars might represent miniature versions of this process, where black holes undergo their own form of cosmic rebirth. This means the universe's own history might be echoed on a smaller scale with the rebirth of black holes. If true, Planck stars could help to unify the behavior of the universe's largest and smallest objects under one theory. The elusive nature of Planck stars makes them nearly impossible to detect directly. They are far too small and occur under extreme conditions, meaning that any physical traces they leave behind are incredibly faint. However, certain gravitational waves or specific bursts of radiation might be a way to detect them. These would be difficult to observe with current technology. But as our understanding and detection tools evolve, we may eventually find clues pointing to these strange objects. But could this really be the future of black holes? As theoretical as Planck stars are, they point to the possibility that quantum gravity, the yet-to-be fully understood combination of quantum mechanics and gravity, plays a major role in the evolution of black holes. Unlike general relativity, which predicts the formation of singularities, quantum gravity might explain how space-time behaves on the tiniest scales, preventing black holes from becoming singularities at all. This brings us to a critical question. Could Planck stars provide the key to uniting quantum mechanics with general relativity? Currently, these two pillars of modern physics do not agree when it comes to understanding black holes. General relativity predicts that singularities form, while quantum mechanics insists information can't be lost. Planck stars suggest a middle ground, where the collapse stops at the Planck scale and information is preserved. If this theory is confirmed, it would be a huge step towards solving one of the most profound problems in modern physics. In the grander picture of cosmic phenomena, Planck stars offer a captivating glimpse into the possible fates of the universe's most extreme objects. They suggest that black holes are not simply dead ends, but instead could be part of a greater cycle of collapse and rebirth. As we continue to explore the nature of black holes, the discovery of Planck stars would not only change our understanding of gravity and quantum mechanics, but also reshape our view of the universe's long-term future. This idea of a cyclic universe, where objects like black holes are reborn and return their energy back to the cosmos, fits neatly into the overarching theme of strange cosmic phenomena. Planck stars, with their potential to resolve long-standing paradoxes and change our understanding of black holes, could become a crucial part of the evolving story of how the universe operates on both the smallest and largest scales. The dying light of quasi-stellar objects, galaxies flickering out like candles. The universe contains mysteries beyond our comprehension, and the narrative of collapsing galaxies is told by the light that is disappearing from quasars. Quasars, which are quasi-stellar objects, are the culmination of the most energetic and dazzling phase of the galaxy's evolution. These old lights shed light on the cosmos's long history, allowing us to see how galaxies once were and how they began to fade away. Supermassive black holes at the heart of galaxies power quasars, which were once the brightest objects in the universe. However, as their host galaxies slowly fade into darkness, the quasar's brightness gradually decreases as well. The quasar's life starts with a galactic merger or intense gravitational disruption, triggering a frenzy of material being funneled toward the central black hole. As this matter falls into the black hole, it forms an accretion disk, an orbiting structure of superheated gas and dust, which generates immense energy. This process of accretion lights up the quasar, and the galaxy becomes one of the brightest objects in the universe. However, the intense radiation from quasars isn't always a sign of growth. Instead, it can signal the beginning of a galaxy's end. As the quasar shines brightly, the powerful radiation and winds it produces push the remaining gas out of the galaxy. These molecular outflows, expelled by the quasar, deprive the galaxy of the raw materials needed for star formation. Without the ability to form new stars, the galaxy gradually ages and fades. The quasar itself eventually runs out of material to feed on. As the central black hole consumes the last of its fuel, the light of the quasar begins to dim and the galaxy falls into a dormant state, no longer active or creating new stars. Both the quasar and the galaxy surrounding it go out as their brightness fades. These galaxies eventually become cosmic ghosts, a state of complete stillness and lack of star formation that leaves behind nothing except the faint traces of their former brilliance. Because it marks the end of a galaxy's active existence, this change is very fascinating. The galaxy gradually fades into oblivion as star creation comes to a halt, and previously produced stars die off over millions of years. High redshifts are a hallmark of quasars, suggesting that these objects are so distant that it takes billions of years for their light to reach Earth. Looking at a quasar is like taking a trip through the cosmos's early days. Ancient artifacts, quasars were most likely produced in the early billions of years following the Big Bang. Their luminosity is a window into the universe's history and the phases of a galaxy's life cycle. They shed light on the history of the universe and the ultimate destiny of galaxies as they gradually fade away. As a source of reionization, quasars are an intriguing feature of the cosmos. The gas between galaxies in the early cosmos was largely neutral until quasars exploded and released powerful ultraviolet light, which ionized the gas and made it charged. The structure of the cosmos was greatly influenced by this time, which is called the epoch of reionization. The role of quasars was crucial in this process, since they illuminated previously dark areas of the cosmos and contributed to the formation of the galactic web that is visible to us today. There are larger implications for dark matter knowledge in the dying phase of quasars. Through gravitational lensing, which occurs when huge objects bend the light from faraway quasars, quasars frequently show that dark matter is present. Dark matter, which would normally be undetectable to the naked eye, may now be studied by astronomers thanks to this phenomena. As they approach oblivion, the light from quasars illuminates the unseen structure of the cosmos, acting as a cosmic flashlight. The strength of the galactic winds produced by quasars decreases as their fuel levels decrease. When these winds that once swept away gas that may have become stars ultimately die out, the galaxy is left gas-free. The silent black hole in the galactic core is still there, but it is no longer actively devouring matter. The galaxy gradually enters a red and dead condition, where only old stars persist, and the formerly dynamic quasar becomes a dwindling remnant. Even today, we observe the remnants of once active quasars in modern galaxies. These galaxies show signs of having hosted quasars, with massive black holes at their centers, but no ongoing quasar activity. These inactive quasars offer a glimpse into what our Milky Way might look like in the distant future, once our galaxy's black hole has consumed all available material. A quasar has a very brief cosmic lifetime, ranging from tens of millions of years to 100 million years. Although this appears lengthy when viewed through a human lens, it constitutes a mere blip on the cosmic timeline. For many quasars, the light we see now is their last radiance before they die out entirely. Their brief yet spectacular lives provide light on the violent processes that formed galaxies and their ultimate demise. Even when they fade away, quasars are still very useful to astronomers. With their light diminishing, they shed light on the gas that fills the space between galaxies, a phenomenon that has long fascinated astronomers. Researchers are making progress in understanding the creation and evolution of galaxies by gaining a better grasp of the characteristics of this gas, which is an essential component in the process. As they fade away, quasars keep on teaching us about the building blocks of the cosmos. The dying light of quasars is more than just a cosmic phenomenon. It is a window into the life cycle of galaxies and the evolution of the universe itself. As they flicker out like candles, quasars leave behind a legacy of discovery, helping us understand the forces that shape galaxies and the ultimate fate of the cosmos. Hypervelocity stars, galactic projectiles fired by black holes. Fired from the chaos of black holes, hypervelocity stars are a mysterious cosmic phenomenon. When two stars orbit each other and stray too close to the monstrous gravity of a black hole, the results are often catastrophic. Instead of being swallowed whole, one star might be launched into space at speeds fast enough to escape its galaxy. The other star is usually devoured by the black hole, but the survivor becomes a rogue traveler, flung across the universe like a cannonball. Imagine the raw power required to eject a star this way. Black holes, known for their inescapable pull, become the very forces that hurl these stars into intergalactic space. This interaction makes hypervelocity stars not just objects of speed, but of terrifying power, a stark reminder of the destructive and unpredictable nature of black holes. Once freed from the confines of their galaxy, these stars no longer follow the rules we know. They break free from the pull of gravity, entering a new and eerie state, roaming forever alone. The escape from a galaxy is more than just a spectacular feat of speed. Hypervelocity stars travel faster than the escape velocity required to leave their galaxy, effectively severing their ties to the cosmic systems they once called home. Most stars remain bound to their galaxies, orbiting its center in harmony with billions of other stars. But hypervelocity stars defy this order. They break free, defying the gravitational hold that controls everything else in the galaxy. It's not just about speed, though. Their isolation in the vast darkness of space is equally unsettling. Without the familiar warmth of other stars and solar systems, they embark on an eternal journey through the cold void, heading toward the unknown. They are not just alone in space. They are utterly isolated in a way that few cosmic phenomena experience. In the terrifying encounter between black holes and binary star systems, the black hole doesn't merely consume, it also accelerates. As the black hole's immense gravity pulls the stars apart, the slingshot effect can be so powerful that it catapults one star away at an insane speed, allowing it to achieve hypervelocity. This phenomenon showcases the black hole's ability to both destroy and energize, turning a star into a high-speed traveler rather than a meal. The collision between these colossal forces leaves a lasting imprint on the universe, as these hypervelocity stars now zip across space without a galactic tether. It is in this delicate balance between destruction and acceleration that black holes reveal another layer of their terrifying nature. The origins of hypervelocity stars are still a puzzle for astronomers. The first was discovered in 2005, traveling at 2.6 million kilometers per hour. Its path was traced back to the center of the Milky Way, where Sagittarius A star, our galaxy's supermassive black hole, likely launched it. But not all hypervelocity stars originate from the Milky Way. Some might have been ejected from distant galaxies, traveling through intergalactic space for billions of years. These cosmic travelers have crossed unimaginable distances, their origin stories hidden in the farthest reaches of the universe. Their intergalactic journeys are a haunting reminder of how little we understand about the mechanisms that govern the cosmos. Unlike most stars, which form within galaxies and are bound by their gravity, hypervelocity stars are often regarded as cosmic loners. They break all the rules, no longer bound to orbit anything or follow predictable paths. While galaxies are structured systems with billions of stars, dust and gas moving in harmony, these stars operate outside that structure, indifferent to the norms. This rogue existence may seem romantic at first, traveling the universe unbound by any force, but it's far from that. These stars are destined to drift in isolation, never forming part of any galaxy again. as they move further from their origin, they leave behind all the familiar structures of the universe and plunge into the truly unknown. The thought of a lone star traveling eternally through a dark, empty universe is enough to send shivers down the spine. The influence of dark matter in the destiny of hypervelocity stars is frightening. We don't yet know how their trajectories will be changed when they go through dark matter-dominated parts of the cosmos. Although dark matter does not interact with ordinary matter as other forces do, it is nonetheless powerful enough to alter the trajectory of these stars due to the gravitational pull it applies to everything it passes through. Another degree of intricacy is added to the voyage of hypervelocity stars by the mysteries of dark matter and its unknown impact on the cosmos. We may never be able to fully understand the influences that form them. A hypervelocity star's journey is both incredibly fast and incredibly lonely. Once ejected from its home galaxy, it will travel through the vast expanse of space, with little to no chance of encountering anything familiar again. These stars, which once belonged to structured solar systems and galaxies, now find themselves in the cold, empty space between galaxies. Their speed ensures that they are constantly moving, but where are they going? Will they ever encounter another star system, or are they destined to drift aimlessly forever? The idea of stars being cast out of their home galaxies and forced to wander through the darkness is both fascinating and terrifying. The trajectory of hypervelocity stars isn't random. They are ejected with such force and precision that they maintain a straight path, but dark matter and the gravitational forces of other galaxies could still alter their routes. In rare cases, these stars might pass near enough to other galaxies to have their paths shifted, though this is exceedingly rare. More often than not, these stars travel through intergalactic space with no obstacles in sight. This uninterrupted journey, combined with their extreme speed, means that hypervelocity stars could continue on their path for billions of years, forever fleeing their origin galaxy. The possibility of entire star systems being ejected from galaxies is a chilling thought. In rare cases, interactions with black holes could eject not just individual stars, but entire systems of stars, planets, and other celestial bodies. These systems, once bound together by gravity, could be hurled into space, turning them into galactic wanderers. Such a system would become a cosmic projectile, its planets and stars careening through space without any anchor. If such a system were to pass through other galaxies or systems, the disruption could be catastrophic, leaving chaos in its wake. While rare, the possibility of such an event occurring adds another level of danger to the already unsettling nature of hypervelocity stars. Hypervelocity stars are characterized by their extremely rapid speeds. These stars are the galactic speed champions, hurtling across space at hundreds of kilometers per second. For context, these stars cross the same distance in a fraction of the time it would take even our fastest spaceship to go that distance millions of years ago. Understanding how they reach such velocities might provide fresh light on the processes that form the cosmos, and their speed makes them distinctive subjects of research. Hypervelocity stars are the fastest objects in the cosmos, surpassing all previous observations of speed. Born from violent encounters with black holes and sent on endless journeys through space, these stars represent the incredible power and chaos that exists in the universe. Their speed, isolation, and unpredictable paths make them some of the most haunting objects in the cosmos. Spontaneous black hole formation. Could a black hole form anywhere at any time? A black hole forming spontaneously sounds like something out of science fiction, but it may be far closer to reality than we think. There are numerous mechanisms throughout the universe that could lead to the sudden creation of a black hole without the traditional death of a star. Quantum fluctuations, high-energy collisions, dark matter, and even vacuum decay are just some of the processes that suggest black holes could appear almost anywhere, at any time. Quantum mechanics, in particular, hints at the possibility that black holes could arise from the smallest of cosmic disturbances. This idea, while abstract, ties into the fundamental nature of the universe itself. In the fabric of space-time, even seemingly empty regions teem with energy fluctuations. These vacuum fluctuations occur on such tiny scales that we usually don't notice them. However, under the right conditions, such as in regions of extreme density or pressure, these fluctuations could theoretically become so intense that they lead to the formation of micro-black holes. These black holes would be extremely small and short-lived, evaporating almost as quickly as they form through a process called Hawking radiation. The idea of primordial black holes suggests that black holes formed in the earliest moments after the Big Bang. Back then, the universe was a chaotic, hot, and dense place, and under such conditions, black holes may have formed without the collapse of stars. These primordial black holes could have been left behind from that turbulent period, scattered throughout the universe like cosmic relics. If they exist, they could explain certain anomalies in our observations, such as mysterious sources of gravitational waves or certain behaviors of dark matter. High-energy particle collisions also offer a window into spontaneous black hole creation. Particle accelerators like the Large Hadron Collider simulate some of the most extreme conditions in the universe by smashing particles together at nearly the speed of light. The goal is to recreate, on a tiny scale, the kind of environment that may have existed just after the Big Bang. Some theories suggest that such high-energy collisions could generate micro-black holes, although none have been detected yet. Nevertheless, the potential remains, pointing toward the idea that under the right circumstances, black holes could form in ways we have not yet fully understood. Dark matter, the mysterious substance that makes up much of the universe's mass, could also play a role in this phenomenon. While we still don't know exactly what dark matter is, some theories propose that its interactions with normal matter could cause areas of extreme density. If these regions become dense enough, they might collapse into black holes. This would provide a new understanding of how black holes form and where they might be hiding, particularly in areas of the universe we currently cannot observe clearly. Even more unsettling is the concept of vacuum decay, which suggests that the universe as we know it exists in a false vacuum state. In this scenario, if the true vacuum were to emerge, it could trigger a catastrophic chain reaction that might collapse parts of the universe into black holes. While this idea remains speculative, it introduces the possibility that black holes could form suddenly and unpredictably, leading to localized collapses of space-time itself. There are exotic ideas that delve into even more speculative realms of physics. For instance, string theory, which proposes that the universe has extra dimensions beyond the familiar 3 of space and 1 of time, suggests that black holes could form in these hidden dimensions. These micro-black holes would be minuscule and nearly impossible to detect, but they could provide insights into the fundamental nature of the universe and its hidden properties. Gravitational waves are ripples in space-time caused by massive objects moving at incredible speeds. When two black holes or neutron stars collide, they release tremendous amounts of energy in the form of gravitational waves. Some scientists theorize that these waves, under the right conditions, could trigger the formation of additional black holes as they interact with space-time itself. This would suggest that black holes could create other black holes, a cascade of collapses that could shape entire regions of the cosmos. The existence of cosmic strings raises the possibility that they play a role in the spontaneous generation of black holes. It is believed that these hypothetical things are remnants of the early universe's fabric of space-time that have become defective. A black hole might be formed by the collision or interaction of two cosmic strings. The fact that cosmic strings may influence the genesis of black holes is a mystery in and of itself, even if we have not yet seen them. According to the second law of thermodynamics, entropy, or the measure of disorder, must always increase. black holes are thought to be the ultimate containers of entropy. As entropy increases across the universe, some theorists suggest that spontaneous black hole formation might become more likely in regions where entropy reaches its maximum. In this view, black holes could be the natural consequence of the universe's tendency toward disorder. Hawking radiation itself presents a paradox. While it predicts that black holes can lose mass and eventually evaporate, it also implies that smaller black holes could form and disappear quickly. This raises the question of whether spontaneous black hole formation could be more common than we think, with these objects appearing and vanishing in the blink of an eye, leaving little trace of their existence. A mysterious element known as dark energy is responsible for the cosmos's rapid growth. Some researchers have hypothesized that variations in dark energy might provide unstable areas where black holes could spontaneously emerge, while the exact nature of these regions is yet unknown. If confirmed, this would point to a connection between black holes and the cosmos as a whole, implying processes beyond what we know about cosmology at the moment. The notion that black holes could form spontaneously without the death of a star challenges our understanding of these objects as mere endpoints of stellar evolution. Instead, it paints a picture of a universe where black holes can emerge from a variety of different processes, from the quantum scale to the vastness of cosmic strings and gravitational waves. The spontaneous creation of black holes may be far more common and far more mysterious than we ever imagined. The Kerr metric: black holes that twist space and time. The Kerr metric describes black holes that spin, introducing some of the most mind-bending consequences in the universe. Unlike non-rotating black holes, Kerr black holes twist space and time, pulling them into a vortex-like shape. The force of this spin alters the surrounding universe in ways that defy the laws of physics as we know them, turning space and time itself into something malleable. The moment you approach one of these rotating giants, you'll be pulled not just inward toward the event horizon, but also sideways, in the direction of the black hole's spin. This is known as frame dragging, a cosmic tug-of-war where even light itself is twisted. It creates a chaotic space around the black hole, called the ergosphere, where nothing can remain still. Everything is forced to spin with the black hole, and this movement distorts the passage of time, blending the boundaries between space and time in a terrifying way. Within the ergosphere, something unusual happens. It becomes theoretically possible to escape from the black hole's grip by exploiting the chaotic energy inside this zone. Through the Penrose process, particles that enter the ergosphere can split in such a way that one half falls into the black hole while the other escapes, gaining more energy than it initially had. This idea has fascinated scientists for years, not just because it suggests an escape from the gravitational pull of a black hole, but also because it raises the question of whether this energy could be harnessed. Could advanced civilizations one day use the energy of a spinning black hole to power their technology? The concept is almost too wild to consider, but the physics checks out. In a way, it makes the Kerr black hole a potential energy source, though it comes with unimaginable risks. The event horizon, the boundary beyond which nothing can be recovered, is located beyond the ergosphere. However, Kerr black holes operate differently even in this case. The event horizon becomes more dynamic and unexpected as a result of the distortion caused by the black hole's spin. While the vast majority of black holes obliterate all in their path, Kerr black holes have the ability to unleash extremely powerful jets of matter and energy. The so-called relativistic jets may disintegrate whole star systems and even galaxies as they accelerate matter to almost the speed of light and launch it across enormous distances. It is an impressive demonstration of power that endangers everything in its vicinity and expands the scope of devastation to cosmic proportions. Kerr black holes may do more than merely sweep the cosmos. They may even be cosmic reapers, wreaking havoc on everything in their path. The singularity at the heart of a Kerr black hole is another bizarre twist on the standard black hole model. While non-rotating black holes have a point-like singularity, Kerr black holes feature a ring-like one, a warped structure that's even harder to comprehend. This ring-shaped singularity warps both space and time, creating what some theories suggest might be pathways through space-time itself. Could these be gateways to other parts of the universe? Or perhaps even to other universes? These ideas bring us into the realm of closed time-like curves, theoretical loops where space and time are so twisted that one could theoretically travel through time. Such concepts push the boundaries of physics and raise the possibility of time travel paradoxes. What if traveling through time becomes possible within a Kerr black hole's influence? The terrifying answer is that we don't know, but the physics suggests it might not be impossible. Kerr black holes aren't just theoretical oddities, they're likely far more common than we think. In fact, many supermassive black holes at the centers of galaxies, including the one at the center of our Milky Way, are likely spinning black holes. Their rotational power doesn't just affect the stars and gas around them, but potentially influences entire regions of space far beyond the black hole itself. The spin adds another layer of complexity to the black hole's gravitational pull, making it even more dangerous and difficult to study. It's like a tornado, but instead of just sucking everything into a single point, it also twists and contorts the very fabric of the universe. As black holes consume more matter, they grow in size and in spin. Theoretically, a Kerr black hole could spin so fast that it reaches the speed of light, a situation that would produce unimaginable consequences for anything nearby. The faster it spins, the more intense the frame-dragging effect becomes, pulling everything around it into a tighter and more chaotic spiral. This raises a chilling question. Could there be a point where the spin becomes so intense that it destabilizes the black hole itself? Some physicists have speculated that the maximum spin of a Kerr black hole could lead to strange, unpredictable phenomena, perhaps even the black hole tearing itself apart or ejecting massive amounts of energy in a burst of cosmic violence. Questions regarding Kerr black holes' impact on the cosmos are further prompted by the matter and energy jets they release. It is possible for these jets, which may extend across hundreds of thousands of light years, to disturb whole galaxies. The energy emitted by these jets has the potential to either stimulate star formation in some locations or eradicate them entirely. These spinning behemoths are incredibly strong and utterly unexpected, as seen on a cosmic scale of devastation and creation. If a galaxy is home to a Kerr black hole, it may have an effect on the galaxy's evolution that goes much beyond its immediate vicinity. Being able to blend in with their surroundings may be the most terrifying thing about Kerr black holes. They are harder to spot than regular black holes due to their rotating properties, which mask part of the light and energy that would otherwise indicate their presence. Because of this, it's not out of the question that adjacent Kerr black holes are bending space-time without anybody noticing. How many of these unseen behemoths may be impacting the cosmos in ways we can't yet fathom? Both the mystery and the terror of the solution are real. We may be oblivious to the fact that these cosmic whirlpools are warping space and time. In a universe already filled with unsettling phenomena, Kerr black holes stand out as one of the most unpredictable and dangerous. Their ability to twist space and time, launch jets of destruction, and potentially open pathways through space-time itself make them more than just massive objects. They're forces of cosmic chaos. And the fact that they could be hiding in plain sight, undetected by our current technology, only adds to the fear. The magnetar threat. Supermagnetic stars that could shred spacecraft. Magnetars are among the most terrible of the many cosmic threats. These stars are always on the verge of catastrophic collapse due to their hypermagnetization and explosive nature. Magnetars have the potential to destroy spacecraft and even nearby stars with their enormous magnetic fields and radiation emissions. Imagine a magnetic field so powerful that it could tear apart the very atoms holding your body together. Magnetars boast magnetic fields up to 1,000 trillion times stronger than Earth's. That's the kind of force we're dealing with when we talk about these stars. For any spacecraft unlucky enough to come within even a fraction of a light-year from one, the effects would be catastrophic. The magnetic pull of a magnetar is strong enough to scramble the electronics of a spaceship long before it gets close. Even the sturdy structures designed for interstellar travel wouldn't stand a chance. Computers would fail, communications would break down, and the spacecraft's hull would start to disintegrate under the immense magnetic pressure. But the damage wouldn't be limited to the spacecraft itself. Any humans on board would face a worse fate. Magnetars emit intense radiation that can alter the atomic structure of human cells, leading to instant cellular destruction. If exposed, an astronaut's very DNA would unravel within seconds, leaving no time for escape or rescue. Magnetars are also known to unleash incredibly violent gamma-ray bursts, GRBs. These explosions are so powerful that one gamma-ray burst releases more energy in just a few seconds than our Sun will produce over its entire lifetime. Thankfully, magnetars are rare and located far away, but even a distant burst could be lethal. What makes gamma-ray bursts particularly terrifying is that they happen without warning. A magnetar, seemingly calm and stable, could suddenly unleash one of these bursts, irradiating anything in its path. If a gamma-ray burst were to hit a spacecraft, even from thousands of light-years away, the burst could fry its systems, wipe out its crew, and leave nothing but drifting debris. Gamma-ray bursts from magnetars are among the most powerful forces in the universe, and if one were directed toward Earth, it could pose an existential threat. The shockwaves would tear through our atmosphere, and the radiation could obliterate life as we know it, leaving behind only scorched remnants of what once existed. A magnetar's extreme magnetic field doesn't just affect physical objects, it could also distort space-time itself. Scientists theorize that the strong magnetic fields of magnetars might warp the very fabric of reality, creating space-time distortions. These distortions could alter the way light and matter behave, making nearby objects appear to bend, stretch, or even disappear. The consequences of such a phenomenon are unimaginable. A spacecraft caught in a space-time distortion caused by a magnetar could be stretched out into nothingness or sucked into a gravitational well, never to escape. Time could pass differently for objects near a magnetar, meaning that minutes on the spacecraft might feel like years for the crew, if they survive long enough to notice. Magnetars also experience starquakes, the result of sudden shifts in their magnetic fields. These quakes are far more intense than anything we could ever experience on Earth. When a starquake happens on a magnetar, it releases an enormous amount of energy, billions of times the energy of the largest earthquake ever recorded on our planet. The resulting shockwaves from these starquakes travel outward at incredible speeds, and if a spacecraft were nearby, it would be torn apart by the sheer force. Even at a distance of millions of miles, these shockwaves can destabilize space probes and satellites, causing them to lose control and careen into oblivion. For astronauts or space explorers, the effects of a starquake would be instantaneous and deadly. The electromagnetic waves generated by the quake could render all electronic equipment useless, leaving the spacecraft to drift aimlessly through space. In the worst-case scenario, the shockwaves could physically tear the spacecraft apart, killing everyone aboard in seconds. Radiation is one of the biggest challenges of space travel, but magnetars take this threat to a whole new level. A magnetar emits radiation at levels that would obliterate any human being caught in its vicinity. The intense X-rays and gamma rays emitted by a magnetar could fry human cells, leading to instant death. For those on board a spacecraft, the radiation would penetrate the hull, making traditional shielding completely ineffective. Even the most advanced radiation protection technology wouldn't be enough to shield astronauts from the sheer amount of energy radiating from a magnetar. Within moments of exposure, the crew would be incapacitated, with no chance of survival. The radiation threat from magnetars is so significant that any future space missions will need to carefully chart courses to avoid these deadly stars. A single miscalculation could result in an encounter with a magnetar, dooming the entire mission before it even has a chance to begin. Magnetars aren't just a threat to spacecraft, they could also pose a danger to other stars. In some binary star systems, magnetars interact with their companion stars, slowly stripping away their material in a process known as cosmic cannibalism. As the magnetar pulls matter from the neighboring star, it grows more massive and more powerful. This interaction between the magnetar and its companion star can lead to the eventual destruction of the star itself. The intense magnetic forces from the magnetar can tear the star apart, leaving behind only remnants of what was once a brilliant celestial object. As the magnetar continues to feed, it grows stronger, increasing its already immense magnetic field and becoming an even greater threat to anything in its vicinity. What's truly terrifying about magnetars is that they can be hard to detect. Their magnetic fields don't emit visible light, and they are often shrouded in the remnants of supernova explosions, making them almost invisible to the naked eye. This means that a spacecraft could accidentally stumble into a magnetar's magnetic field without realizing it until it's too late. Even if astronomers detect a magnetar from a distance, the magnetic storms it unleashes can travel far beyond the star itself, creating a massive radius of danger. Future space exploration will require advanced detection systems capable of pinpointing magnetars and avoiding them at all costs. But until then, the lurking threat of these invisible death traps remains a constant concern. Magnetars may not stay magnetars forever. Under the right conditions, a magnetar could undergo gravitational collapse, transforming into a black hole. As the magnetar collapses, it releases an enormous amount of energy, creating shockwaves that would obliterate anything in the surrounding area. For any spacecraft nearby, the formation of a black hole from a collapsing magnetar would be an inescapable death sentence. The gravitational pull of the newly formed black hole would trap any object in its vicinity, pulling it toward the event horizon, where it would be stretched out and destroyed by tidal forces. The formation of a black hole from a magnetar could also have far-reaching effects, sending shock waves through space and potentially disturbing nearby star systems. This process, though rare, is a grim reminder of the destructive potential of magnetars and the dangers they pose to space exploration. White hole paradox. The reverse of black holes that may exist. White holes are theoretical objects that have baffled scientists since they were first predicted by the same equations that describe black holes. If black holes are cosmic vacuums that suck in everything, including light, white holes are their mysterious opposite. They would eject matter and energy with no apparent source and permit nothing to enter. Their existence remains speculative, but they challenge our understanding of space, time, and the fundamental laws of physics. Strangest features of white holes is that they could theoretically release massive amounts of energy without drawing in any matter. Black holes, for example, grow by devouring surrounding stars, gas, and even light itself, their immense gravitational pull drawing in everything nearby. But imagine an object that does the opposite, expelling energy and matter outward with nothing able to enter. This concept is not just bizarre, it defies the way we typically think about how energy works in the universe. White holes suggest the possibility of an object that doesn't need to consume anything to generate explosive amounts of radiation. Some scientists speculate that if white holes existed, their energy emissions would be short-lived and incredibly violent. They could be responsible for sudden intense bursts of gamma rays or other radiation that we've yet to fully understand. While we've observed such events, their sources remain mysterious. Could they be white holes erupting in distant parts of the universe, flaring up before collapsing into nothingness? The unpredictability and randomness of such an event make it even more chilling. Black holes, despite their ravenous appetite, slowly evaporate over time, a process known as Hawking radiation. Theorists have suggested that as black holes reach their final stages, they may start to behave more like white holes, ejecting matter and radiation in explosive bursts. Could it be that white holes aren't entirely separate from black holes, but rather the final stage of a black hole's life cycle? If true, this would mean that black holes eventually stop consuming and begin ejecting all the matter they've gathered over the course of their existence. Instead of remaining silent forever, black holes might explode into white holes, spewing matter back into the universe. The horrifying implication is that even the seemingly endless hunger of black holes has a limit, and once reached, the process reverses, turning these galactic predators into cosmic vomiters, ejecting everything they've absorbed. This concept adds another layer of terror to the notion of black holes, as it suggests their eventual death throes would be equally, if not more, destructive than their life cycle. Some cosmologists propose an even more mind-bending theory, that the Big Bang itself could have been the result of a massive white hole. In this scenario, a white hole would have expelled all the matter that created our universe in a single cataclysmic event. This notion would not only explain the vast amount of matter ejected in the Big Bang, but it would also suggest that white holes may be responsible for creating entire universes. If white holes can create universes, then every black hole we observe could potentially lead to the creation of new universes. Picture it, our own universe being just one in an infinite chain, each born from a white hole, formed in the collapse of another universe's black hole. This cyclic model of universal creation is staggering in its implications, and it blurs the line between destruction and creation. Rather than being mere endpoints, black holes and white holes could be the engines that drive the multiverse, constantly destroying and creating universes in an endless loop. What happens to data, such as particle states, that goes into a black hole is one of the biggest mysteries surrounding these mysterious objects. Classical physics states that information cannot be destroyed. Nevertheless, black holes appear to defy this law. White holes might be the answer. Could black holes, like white holes, spew materials, including data that was previously believed to be lost? This notion turns on its head the horrifying thought that a black hole may destroy everything. White holes don't spell doom, but rather a glimpse of optimism, because data is just temporarily sucked in before being spit back out. The terrifying prospect of colliding with a black hole is further complicated by the possibility that white holes may store data sent by black holes. What goes in must come out, even if it takes millennia and takes a completely other form. It hints to a cosmic balancing act. Unlike their black hole counterparts, which can persist for billions of years, white holes might be fleeting phenomena. Some models suggest that white holes would be extremely unstable, existing only for a short time before collapsing into themselves or dissipating. This could explain why we haven't yet detected one directly. If they do exist, their brief lifespans make them elusive, like cosmic ghosts that flash into existence before disappearing again. These short-lived eruptions would likely release immense amounts of radiation and energy, enough to make even a brief appearance deadly. A white hole bursting into existence near a planet or star could cause catastrophic damage in an instant, vaporizing anything nearby. The unpredictability of these potential bursts adds to their horrifying nature, making them impossible to anticipate or avoid. The most exciting possibilities is that white holes might act as portals to other universes. If black holes suck matter into a singularity, could white holes eject it into another dimension or universe? This theory has its roots in the concept of wormholes, hypothetical tunnels through space and time that connect distant points in the universe, or even different universes altogether. The connection between black holes and white holes hints that these objects could be the entry and exit points of such tunnels. If true, This would mean that every black hole has a corresponding white hole on the other side, acting as a cosmic bridge between different realms. The notion that white holes could spew matter into unknown universes is both awe-inspiring and terrifying. It raises the unsettling question, what's on the other side, and could something be coming through? Though we have yet to observe a white hole directly, some scientists suggest that they might leave traces in the form of gravitational waves. Just as black holes merging create ripples in space-time that we can detect, a white hole erupting into existence could also produce gravitational waves. These waves would be distinct from those caused by black hole mergers or neutron-star collisions, offering a unique signature that could reveal the presence of a white hole. If we were to observe such an event, it would confirm the existence of these enigmatic objects and open up a new chapter in our understanding of the universe. However, the discovery of a white hole would also raise troubling questions about the stability of our universe. If white holes can randomly burst into existence, what's to stop one from forming near Earth, unleashing catastrophic energy in our direction? The thought of encountering a white hole is equally frightening, albeit in a different way. A spacecraft or planet approaching a white hole would be repelled by its intense energy and radiation. Anything getting too close would be flung away at incredible speeds, possibly torn apart by the sheer force of the ejection. The hemorrhaging pulsars, stars losing mass at alarming rates. Hemorrhaging pulsars represent some of the most intense and mysterious phenomena in the cosmos, fitting perfectly within the theme of cosmic horrors. These stars are not just spinning at unimaginable speeds, they are actively losing mass at an alarming rate, creating vast nebulae in the process. The mechanisms behind their mass loss are varied, often violent, and poorly understood. From magnetic decay to binary star systems pulling them apart, these cosmic remnants serve as a stark reminder of how chaotic and destructive the universe can be. Unlike stable stars like our Sun, pulsars are born from the remnants of massive stars that went supernova. After such a violent explosion, what's left is a neutron star, an incredibly dense object about the size of a city, but with a mass greater than the Sun. Pulsars are a type of neutron star that spins rapidly, emitting beams of electromagnetic radiation that sweep across the universe like lighthouse beams. These rotating stars, however, don't always remain stable. Many of them undergo rapid changes in their mass and magnetic fields, leading to their destruction. The idea that a pulsar can lose mass so violently challenges many of our assumptions about stellar remnants. Some of this mass loss can be traced back to the decaying magnetic fields surrounding the pulsar. Magnetic fields in pulsars are incredibly strong, millions to billions of times stronger than Earth's. These magnetic fields slow down the pulsar's spin over time, but as they decay, the star begins to lose its grip on the material it's holding. Like a spinning top losing momentum, it begins to wobble and throw off mass in bursts, creating trails of matter that expand into space. These expanding trails, known as pulsar wind nebulae, can be viewed as cosmic blood trails, indicating just how much mass has been lost. A pulsar's mass loss often results in the formation of a pulsar wind nebula. These nebulae are made up of high-energy particles, ejected from the pulsar and accelerated to nearly the speed of light. Over time, these particles create massive, glowing bubbles of material that expand outward into space. The larger the nebula, the more mass the pulsar has hemorrhaged over time. These nebulae are not static. They grow and change shape as the pulsar continues to lose mass, making them a visual marker of a pulsar's deteriorating state. What's particularly alarming about these phenomena is the speed at which they can occur, far faster than traditional stellar evolution models would predict. The loss of mass is triggered by gravitational interactions in binary star systems. A binary star system contains two stars that orbit around a common center of mass. When one of the stars in the system is a pulsar, its extreme gravitational pull can affect its partner, often leading to mass transfer. The stars essentially engage in a cosmic tug-of-war, with the pulsar either losing mass to its companion or consuming mass from the other star. These interactions often result in sudden bursts of mass loss from the pulsar as the intense gravitational forces destabilize it. The effects of these interactions can be catastrophic, significantly altering the masses and lifespans of both stars involved. Supernovae and other devastating cosmic disasters may have their origins in hemorrhagic pulsars. Although the majority of pulsars are predicted to gradually fade away over millions of years, these ones that are degenerating at a quick pace might cause abrupt and violent terminations. One of the most powerful and devastating forces in the cosmos, a gamma-ray burst, might be ignited, or the pulsar could collapse into a black hole if its mass loss rate is sufficiently high. These hypothetical situations show how hazardous and unpredictable hemorrhage pulsars may be, although they are still in the realm of theory. The possible connection between these mass-shedding stars and gravitational waves is one of the most intriguing elements about them. A phenomenon that was initially postulated by Einstein and has only lately been validated by measurements. Gravitational waves are like ripples in space-time. The acceleration or change in mass of large objects in space causes these waves. Gravitational waves may originate in part from the rapid mass loss that hemorrhagic pulsars undergo. They may produce Earth-detectable spacetime disruptions when they spew matter and alter their mass distribution. Since of this, hemorrhaging pulsars are much more intriguing to investigate since they might be the focus of future gravitational wave investigations. As these stars shed their mass, they move closer to the critical threshold required to collapse into a black hole. While neutron stars have traditionally been thought of as stable endpoints in a star's life, the idea that a pulsar could bleed out into a black hole adds a terrifying new dimension to their story. It raises questions about how many other black holes in the universe may have formed not from massive stellar collapses, but from slowly decaying pulsars that reached a point of no return. Both the local environment and the galaxy as a whole can be profoundly affected by hemorrhaging pulsars. As these stars continue to deplete their mass, they unleash a barrage of radiation and energy that can collide with neighboring objects. The abrupt emergence of these cosmic death throes has the potential to destabilize entire stellar systems, impact nearby stars with radiation, and alter gas clouds. We are merely scratching the surface of the forces at work in this ever-changing cosmos, and this serves as a sobering reminder that nothing stays the same for very long. The fact that a large number of these pulsars are situated within our own galaxy. They pose a greater threat since they may be considerably closer to Earth than other further away celestial events. Just thinking about these stars speeding away at lifeblood is terrifying. It goes to show that the cosmos is filled with cosmic threats that might impact our solar system at some point. Although the likelihood of a pulsar striking Earth is low, the presence of such things highlights how delicate the cosmos is. While theories abound, from decaying magnetic fields to violent gravitational interactions, the truth is that we still don't fully understand what causes some pulsars to hemorrhage mass at such alarming rates. What we do know, however, is that these stars provide a unique window into the life cycles of the most extreme objects in the universe. Their study is essential not just for understanding how stars live and die, but also for uncovering the deeper mysteries of how the universe itself evolves over time. As we continue to learn more about hemorrhaging pulsars, one thing becomes clear. The universe is far from the serene, unchanging expanse it may seem to us here on Earth. It's a place of constant violence, decay, and transformation. These pulsars, shedding their mass into the cosmos, serve as a stark reminder of just how much we still have to learn about the forces that shape our universe. Eridanus, supervoid, a cold, empty patch that defies physics. The Eridanus supervoid stands as one of the most perplexing phenomena in the cosmos, a vast expanse stretching across approximately 1.8 billion light-years, devoid of galaxies and other matter. Its formation may offer insights into the gravitational pull of dark energy, suggesting that it could be a remnant of the universe's evolution influenced by the mysterious forces shaping cosmic structures. As researchers delve into the nature of this enormous void, the implications extend beyond mere size. They challenge our fundamental understanding of the universe. In the heart of the Eridanus supervoid lies a striking absence of galaxies. This peculiar phenomenon raises questions about the distribution of dark matter and how galaxies form in the universe. While galaxies typically cluster together, the supervoid's sparse population of celestial bodies highlights the complexity of cosmic evolution. One theory suggests that this void's formation could be linked to gravitational interactions with surrounding structures, pulling matter away and creating an expansive, empty region. The Eridanus supervoid serves as a cosmic puzzle, shedding light on the processes that govern galaxy formation. Interestingly, the supervoid's existence coincides with anomalies in the cosmic microwave background, CMB, particularly the so-called cold spot. This area, cooler than the surrounding regions, suggests that the uniformity of the universe might not be as absolute as previously thought. Researchers posit that the cold spot's unusual temperature could result from the Eridanus supervoid, which acts as a large-scale lens, affecting how cosmic background radiation propagates. This connection underscores the supervoid's role in reshaping our understanding of cosmic structures and the very fabric of space-time. Void structures, like Eridanus, may play a significant role in shaping the universe's large-scale structure. They can affect the movement and clustering of galaxies, leading to a greater understanding of how matter interacts on a cosmic scale. By analyzing the properties of the Eridanus supervoid, scientists can glean insights into the dynamics of cosmic expansion, potentially revealing clues about the future trajectory of the universe itself. The unique phenomenon of gravitational lensing is also brought to light by the investigation of the Eridanus supervoid. The bending of the course of light across space is caused by large formations like voids or clusters of galaxies. The mass distribution inside and surrounding the Eridanus supervoid has been studied using gravitational lensing techniques. Dark matter may be present and affecting the structure and effect of even apparently empty regions, according to the studies. These gaps might be the result of topological flaws in spacetime that existed during the inflationary era of the cosmos, according to some researchers. This theory begs the interesting issues of how the universe has evolved and what processes have resulted in the creation of such enormous vacuums. Gaining insight into these processes has the potential to completely transform our understanding of the universe's history and complex mechanisms. The consequences for astrophysics are becoming increasingly significant as experts work to unravel the riddles of the Eridanus supervoid. This supervoid's unusual characteristics make it an ideal testbed for cosmological hypotheses. Scientists can get fresh insights into the universe and improve current theories by analyzing the behavior of light and matter in low-density settings. Our understanding of the universe's complexity is enhanced by this inquiry, which highlights the complex interaction between different cosmic events. Our view of the cosmos and our role in it has been profoundly altered by the finding of such vast gaps. By discovering previously unknown aspects of the universe, astronomers are forcing us to re-evaluate our fundamental beliefs. We are philosophically prompted to think on the nature of reality and our comprehension of life beyond Earth by the existence of supervoids, which challenges us to confront our position in an ever-expanding cosmos. The Eridanus supervoid's properties may also touch on the unresolved mystery of matter-antimatter asymmetry. Researchers speculate that the conditions within supervoids could provide insights into why our universe is predominantly composed of matter, despite theories suggesting that matter and antimatter should have been created in equal amounts during the Big Bang. By examining the dynamics of the Eridanus supervoid, scientists hope to uncover potential links to this fundamental question in particle physics. Vast emptiness of the Eridanus supervoid raises questions about the conditions that favor the emergence of life elsewhere in the universe. If such colossal voids exist, what does this mean for the distribution of habitable zones around galaxies? The interplay between cosmic structures, voids, and the potential for life adds an intriguing layer to the investigation of the Eridanus supervoid and its relationship to the broader cosmos. The characteristics of this supervoid may offer critical evidence for understanding dark energy, particularly in terms of its effect on cosmic structures. As scientists piece together the puzzle of the Eridanus supervoid, they seek to clarify the influence of dark energy on cosmic evolution, ultimately shedding light on the fundamental forces that govern the universe. The Galactic Reapers, stars consumed by black holes. Black holes are known as cosmic reapers, capable of tearing stars apart in a slow, inevitable process that defies the laws of nature as we know them. As stars venture too close to these gravitational monsters, they face a phenomenon called tidal disruption. The star's once perfectly shaped sphere gets stretched, twisted, and ultimately shredded apart. The black hole doesn't consume the entire star at once. It methodically devours portions, ejecting the remaining material in dramatic bursts of radiation. These tidal disruption events can be seen across the cosmos, their light a haunting signal of the black hole's destructive power. Another terrifying aspect of a black hole is its event horizon, a threshold beyond which nothing can escape, not matter, not light, and not even our sense of time. The moment a star passes beyond this point of no return, it is no longer visible to the naked eye and becomes an ethereal spectre. Beyond this unseen barrier, there is no way out, no way to survive. Because the star's substance has been swallowed by the black hole, it is as if the star never existed. Adding the process of spaghettification makes this even scarier. A cosmic noodle effect rips the star microscopically apart as it draws nearer to the black hole, stretching it into long, thin threads due to the difference in gravitational attraction between its nearer and further sides. We can comprehend the bleak mechanics of this process, even if no one has ever seen it happen in real life. As they spiral into the black hole's center, the star's atoms are sucked out one by one. All that's left of the star is a whirlwind of gas before it becomes engulfed. Supermassive black holes, like the one in the center of our Milky Way galaxy, are the largest predators in the universe. These monsters, millions or even billions of times the mass of our Sun, lie at the heart of most galaxies, acting as gravitational anchors. But their presence is anything but passive. Stars, gas clouds, and even entire solar systems can fall victim to their gravitational pull, their mass added to the growing black hole as it continues to feed. This process, slow but inevitable, makes the galactic core a dangerous neighborhood for any star that wanders too close. Before the star is completely consumed, its remains form an accretion disk, a swirling vortex of superheated gas and stellar debris. This disk can glow brighter than the entire galaxy around it, radiating energy as the matter spirals faster and faster toward the black hole's center. It's a violent process, marked by chaotic eruptions of radiation and light. These disks are among the brightest objects in the universe, but their luminosity is a signal of cosmic death, the last breath of a star as it's torn apart by forces beyond imagination. Jets of energy, sometimes released from black holes as they feed, are another terrifying feature. These jets, traveling at nearly the speed of light, shoot out into the cosmos, wreaking havoc on any nearby objects. Entire star systems can be disrupted by the passage of one of these relativistic beams, which carry enough energy to scorch planets and alter the trajectories of distant stars. These jets are an eerie byproduct of the black hole's feeding process, a reminder that even as black holes consume, they continue to affect the universe around them. Quasi-stellar objects, or quasars, are one of the most extreme results of a black hole's hunger. Powered by supermassive black holes, quasars emit light and energy that can outshine entire galaxies. The material in the accretion disk spirals inward so rapidly that it generates immense heat, causing the surrounding area to glow with intense brightness. Yet behind this dazzling display lies destruction. The black hole continues to devour everything within reach, leaving behind a flickering beacon that slowly fades as the material is consumed. Black holes can also feed in more subtle ways, such as slowly siphoning off the mass of nearby stars. These stars may not be consumed all at once, but they are destined for a slow death, with their mass gradually pulled into the black hole. This galactic snack leaves the star dimmed and weakened, a shadow of its former self. Over time, the star's light will fade entirely, leaving the black hole as the sole survivor in this deadly interaction. In binary star systems, the death of one star is especially tragic. These systems often contain two stars orbiting one another, bound by gravity. But when one star is consumed by a black hole, the remaining star is forced to continue its orbit, a lone witness to the destruction of its companion. The gravitational forces at play ensure that the surviving star remains in orbit, unable to escape, even as its partner is erased from existence. This slow, torturous dynamic reveals the true horror of black holes as cosmic reapers. When black holes consume stars, they also leave behind echoes of their destruction in the form of gravitational waves. These waves ripple through space-time, carrying the signature of the violent interaction. They provide a window into the cataclysmic events that occur as black holes tear stars apart. Though these waves are faint and difficult to detect, they hold the key to understanding the nature of black holes and their relationship with the universe. The destruction of stars by black holes is a cosmic ballet of violence and beauty. These celestial predators operate on scales beyond human comprehension, yet their actions shape the universe in profound ways. Through tidal disruption, spaghettification, accretion disks, and gravitational waves, black holes reveal themselves as the ultimate force of destruction in the cosmos. Zombie stars, white dwarfs that refuse to die. Stars aren't supposed to live forever. When they run out of fuel, the end is usually violent. A supernova, a collapse into a black hole, or maybe for some, a slow fade into a dark and cold corpse. But for white dwarfs, fate is more complicated. They don't simply die, they linger, sometimes for trillions of years, defying their death like cosmic zombies. Some manage to reignite briefly, while others cool in silence. But how do these zombie stars, white dwarfs that refuse to die, challenge the universe's rules? White dwarfs are the remnants of stars that weren't massive enough to collapse into black holes. The star's outer layers get blown away, leaving behind their small, dense cores. For many, this is the end of their story. But when a white dwarf exists in a binary system, the game changes. The companion star becomes the target of the white dwarf's survival strategy. It's a grim form of cosmic cannibalism. A white dwarf in a binary system starts to draw material from its companion. It doesn't need to be aggressive about it. The process can take millions of years. Hydrogen from the companion star seeps slowly into the white dwarf's atmosphere, fueling bursts of nuclear fusion. This stolen fuel can reignite the white dwarf, leading to a nova. These novas aren't enough to destroy the star. Instead, they allow it to keep existing, like an undead star clinging to life. But even this form of existence isn't permanent. The star is living on borrowed time. When a white dwarf keeps accumulating mass from its companion, there's a limit to how much it can take before the consequences become catastrophic. Once it crosses 1.4 times the mass of the Sun, called the Chandrasekhar limit, the pressure becomes too much. At that point, the star collapses, triggering a runaway fusion reaction that leads to a Type Ia supernova. These explosions are among the brightest events in the universe, capable of outshining entire galaxies. But it's eerie that some white dwarfs sit just on the edge of this limit, managing to stave off destruction for eons. They continue siphoning mass, teetering on the brink of annihilation, but refusing to tip over. Not every white dwarf is destined to explode in a supernova. The quieter ones, without a companion star to feed on, gradually cool down. They don't fade quickly, but enter a slow dimming process, that can take trillions of years. They become black dwarfs, cold and invisible, stars that have finally given up the fight. It's a paradox of extremes. Some white dwarfs die in some of the universe's most violent explosions, while others silently freeze over, no longer emitting light or energy. Within some of these white dwarfs, the quiet tension of carbon and oxygen buildup becomes a cosmic time bomb. If carbon fusion is triggered, it can lead to a detonation that rapidly tears the star apart. The chain reaction is swift and unstoppable. Yet, some white dwarfs remain in a precarious balance, their carbon cores poised on the edge without crossing into the chaotic destruction of a supernova. There's a stark difference between a nova and a supernova. A nova happens when a white dwarf temporarily reignites from the fuel it's stolen, but a supernova means the end of the line. The former is like a star briefly coming back to life, an undead star flaring up before settling back into its slow decline. A supernova, though, is the ultimate and final death. Zombie stars might ignite several times in a series of nova events without ever reaching the supernova stage, prolonging their existence indefinitely. In their last stages, as white dwarfs cool down, something unexpected happens inside them. Their cores begin to crystallize. The atoms start organizing into a solid structure, effectively freezing the star's interior. White dwarfs may eventually become giant diamonds in space. Trillions of years from now, they'll be cold, dead, and glittering. Crystallization slows the cooling process, meaning these undead stars can linger even longer than expected, holding on to their form in a bizarre cosmic afterlife. The white dwarfs that don't crystallize and keep living like zombies get their energy from the stars that orbit nearby. If there wasn't a star nearby for them to eat, they'd just cool off and disappear. White dwarfs become celestial vampires when they rely on another star to keep them alive, and they need a steady supply of hydrogen to do so. They die stealthily without each other in this predatory dance. There are times when white dwarfs have one last dramatic event. They become rogue white dwarfs after being ejected from their binary system, which can happen in supernova explosions or severe ejections. Even though they can't take in any more material, these dead stars are racing through space, telling the tale of their lengthy life. Due to their tremendous velocity, they devolve into nomadic artifacts of the zombie star phenomenon. The unpredictable behavior of white dwarfs has real consequences for how we measure the universe. Type Ia supernovae, caused by exploding white dwarfs, are used as standard candles to gauge vast distances. Their predictable brightness allows astronomers to calculate how far away galaxies are. But what happens if a white dwarf delays its explosion, or if the explosion occurs differently than expected? These deviations can skew the measurements, potentially altering our understanding of the universe's expansion. There's an odd theory that some white dwarfs could have become black holes, but didn't quite make it. Maybe they were massive enough to collapse into black holes, but lost too much mass along the way. This could explain why some zombie stars seem capable of holding vast amounts of matter without triggering their collapse. Stuck between being a black hole and a normal star, they exist in a strange liminal space, neither fully dead nor truly alive. Some researchers speculate that white dwarfs might support life on orbiting planets. While they are dead stars, their gravitational pull could keep planets in stable orbits. In certain conditions, remnants of life from the system's earlier stages might still exist on these planets. If so, these undead stars would host ghostly planets, worlds that continue circling a dead star, perhaps harboring the last traces of life in an otherwise dying solar system. These strange zombie stars challenge our understanding of stellar death and survival. Their persistence and unpredictability make them a vital part of the cosmic story. Stars that refuse to fade, refuse to die, and in doing so, continue to haunt the universe. Just like other cosmic phenomena that defy natural laws, these white dwarfs fit into the overarching theme of cosmic entities that stretch our comprehension of space, time, and life itself. Quintessence, the dynamic dark energy that might rip the universe apart. One of the most mind-boggling concepts in the field of cosmology is the concept of quintessence. It recasts dark energy as an ever-changing power, changing our perspective on its ultimate destiny, rather than a static force. The concept of quintessence raises exciting but disturbing new questions regarding the fate of our cosmos, even if it is based on the enigma of dark energy. We should investigate what this cosmic mystery may mean. Unlike the widely accepted notion that dark energy is static, quintessence offers a more fluid, time-varying solution. In traditional models, dark energy is treated like a constant, the same force that has been pushing the universe apart since its early days. However, quintessence allows dark energy to evolve over time, changing in intensity and impact. This means the very fabric of the universe could be experiencing shifting forces that we've barely begun to understand. The most horrifying idea linked to quintessence is the possibility of the Big Rip. If quintessence causes dark energy to grow stronger over time, it could accelerate the universe's expansion to such an extent that galaxies, stars, and even atoms are torn apart. Picture this: an invisible force that begins to pull everything apart, not just on a galactic scale, but down to the smallest atomic levels. The expansion doesn't stop with space between galaxies. It stretches everything. Eventually, gravity, the force that holds planets in orbit around stars and stars in orbit around galaxies, gets overpowered. Even planets would be shredded into nothingness, and atoms themselves would unravel. The foundation for this terrifying scenario comes from how quintessence interacts with the scalar field, a fundamental entity that defines the behavior of quintessence itself. In physics, scalar fields are mysterious forces that don't behave like the fields we're more familiar with, such as electromagnetic fields. The scalar field involved in quintessence evolves over time, changing the very properties of the universe. Some scientists believe that understanding how these fields work could unlock the secrets of dark energy, but for now, they remain elusive. Interestingly, quintessence might also help solve one of cosmology's great puzzles. Why does dark energy seem to have just the right value to explain our current universe? This is known as the fine-tuning problem. Quintessence suggests that this seemingly perfect balance might only be a temporary phase. Dark energy's effects may not have always been the same and could continue changing in the future, meaning the universe we observe today might be just a fleeting moment in the cosmic timeline. This dynamic behavior adds to the idea that the universe is constantly evolving, and the forces driving this change might not be as fixed as we once thought. But quintessence also touches on another troubling idea: the coincidence problem. Why does dark energy only now appear to dominate the universe? After all, it's been around since the Big Bang, but we're only noticing its effects in recent times. The key could lie in quintessence's evolving nature. Its dynamic qualities might have caused dark energy to rise in prominence only after galaxies had formed and life had evolved to observe it. This raises deep questions about our place in the universe. Are we witnessing a unique phase of cosmic evolution, or is this just a passing moment in a much grander timeline? Phantom quintessence, where dark energy becomes so powerful that it doesn't just expand the universe but breaks it apart entirely. This version of quintessence is beyond frightening. If it exists, the ultimate fate of the universe could be a complete dissolution of space-time itself. In this scenario, quintessence doesn't just stretch the universe to its breaking point, but tears apart even the underlying structure of reality. Space and time could cease to exist in their current forms, and the laws of physics as we know them could collapse. Some theories suggest that it wasn't just a late-game player in cosmic evolution, but might have influenced the earliest moments after the Big Bang. If quintessence was active during the universe's inflationary period, it could have helped shape the rapid expansion that created the universe as we see it. This opens the door to the idea that dark energy, in its quintessence form, has been a driving force since the very beginning, setting the stage for everything that followed. While the cosmological constant, the traditional model of dark energy, acts independently of other forces, quintessence may not be so isolated. Some models suggest that it could interact with gravity or even electromagnetic forces, altering the behavior of particles and light across vast cosmic distances. These interactions could create effects that might be observable in ways we haven't yet understood, possibly leading to new discoveries about the fabric of the universe. This means that instead of staying constant, like the cosmological constant, quintessence changes as the universe evolves. Its energy density might increase or decrease based on factors we don't fully understand, creating fluctuating effects that make the future of the universe unpredictable. We may be living in a brief window where quintessence's effects are balanced, but that balance could shift at any moment, drastically altering the trajectory of the cosmos. Finding a way to witness quintessence in action is the true test. Astronomers are already on the lookout for indications, albeit it remains elusive, much like dark energy. A shift in the rate of cosmic expansion might be a clue that quintessence is influencing the universe. Therefore, scientists are looking for it in faraway supernovae, galaxy clusters, and the cosmic microwave background. We may first learn if quintessence is more than a hypothesis if we notice minor changes in the speed of galaxies or the way light bends over long distances. A number of academics have speculated that the effect of quintessence, as well as the underlying forces that control matter and energy, may be revealed by forthcoming findings about the quantum behavior of particles. The reality of quintessence changes our perspective on the ultimate destiny of the cosmos, and also changes how we see dark energy. A quick and abrupt cosmic shift may be imminent, rather than a gradual descent into a frigid, empty cosmos. The implications of quintessence are vast and profound, raising more questions than answers. Is it responsible for the accelerating expansion of the universe? Could it be the key to understanding dark energy's true nature? Or will it one day tear the universe apart, leaving nothing behind? Primordial black holes, remnants of the universe's violent birth. Primordial black holes, PBHs, are believed to be remnants from the universe's violent birth during the Big Bang. Their existence hints at a connection to some of the earliest moments in our universe. Unlike the supermassive black holes we see at the centers of galaxies today, these ancient objects may have formed in the chaotic conditions of the early universe, potentially just moments after the Big Bang. Understanding PBHs gives us insight into both the nature of black holes and the very fabric of space and time. Primordial black holes are fascinating due to their massive size. They may hold enormous quantities of mass despite varying sizes, from things as little as an atom to things as big as mountains. This size difference may have resulted from variations in density during the early universe's development, which would indicate a distinct formation process. Because the distribution of stuff was not uniform, certain areas may have compressed into these little particles. As the first cosmic structures started to take shape, the development of PBHs may have also acted as seeds around which galaxies grew. Dark matter is known to make up a significant portion of the universe's mass, yet it remains largely invisible to us. Some researchers have proposed that PB8s could account for a portion of this elusive substance. If true, the existence of these ancient black holes could provide a glimpse into understanding dark matter's role in the universe's evolution. PBHs are not just static objects, they are dynamic and subject to the laws of physics. One of the fascinating aspects of black hole physics is Hawking radiation, theorized by physicist Stephen Hawking. This process suggests that black holes can slowly lose mass over time, potentially leading to their eventual evaporation. For primordial black holes, which might be relatively small, this evaporation could occur on shorter timescales. As they lose mass, they may emit bursts of high-energy radiation, which could be detectable from Earth. These emissions might offer a way to observe these ancient entities and validate their existence. There are substantial obstacles to detecting primordial black holes. Direct observation is still a challenge. Currently, researchers are trying to pin down any indirect impacts that would indicate their existence. For example, information may be gleaned by gravitational lensing, which involves the bending of light from faraway objects around huge PBHs. Furthermore, LIGO and similar sensors may be able to detect gravitational waves generated by merging PBHs. Gravitational waves that have been discovered so far may provide evidence of these early black holes. Inflation, the era of the universe's fast expansion, is crucial to the plot of PBHs. Theoretically, primordial black holes formed in certain places and comparatively empty spaces in others during this inflationary phase due to the emergence of dense regions. With galaxies developing around these old remains, this uneven distribution of matter laid the groundwork for the cosmic scenery we see today. The potential implications of primordial black holes extend beyond just understanding the early universe. Some researchers speculate that PBHs could contribute to catastrophic cosmic events. Their presence might destabilize regions of space or influence the formation and collapse of larger cosmic structures. Such dynamics could lead to a more turbulent universe, filled with unforeseen consequences as these black holes interact with their environment. An intriguing new line of research might be to establish a connection between primordial black holes and white holes, which are hypothetical entities that emit matter instead of absorbing it. Time and space, according to certain ideas, are interrelated phenomena that may be better understood if we could establish a connection between the two. Connecting PBHs to white holes might lead to the discovery of extra-dimensional realms or hitherto unexplained cosmic occurrences, by implying the presence of alternate universe routes. Many problems about primordial black holes have not yet been resolved because the field is relatively new. How did they function in the early cosmos? And what is their relationship to dark matter? Gaining knowledge of PBHs might lead to the discovery of long-lost secrets of the cosmos. Scientists are keeping their fingers crossed that further investigation into these mysterious particles will reveal more about the intricate process of cosmic development. Primordial black holes stand out as fascinating relics of the past. Their potential connection to the Big Bang and the evolution of cosmic structures continues to intrigue researchers and laypeople alike. The ongoing quest to understand these ancient entities could lead to groundbreaking discoveries. The Great Galactic Bootes Void, a void larger than anything in the observable universe. The Bootes Void is a terrifying outlier in the visible cosmos, standing alone in the blackness of space. This enormous barren region, which spans more than 250 million light-years, defies all predictions of cosmic dispersion due to its extremely low matter content. Bootes appears hauntingly lonely, contradicting the rules of physics in more ways than one, in contrast to other cosmic gaps that usually include clusters of galaxies. This void isn't just empty, it's a puzzle. In the normal cosmic web, galaxies are arranged along filaments, with voids being natural empty spaces between them. However, Bootes is more than just a gap. It's an extreme anomaly. Imagine standing in a field filled with trees, and suddenly you come across a massive clearing with nothing in sight for miles. That's the Bootes Void. The reason for its emptiness is still unclear, and the lack of galaxies within its stretch leads to questions about how such a vast region could exist in a universe where matter is supposed to be relatively evenly distributed. The creation of this massive void might be linked to the universe's birth. There's a possibility that it is a leftover remnant from the primordial era, a period when the universe was less structured and density fluctuations were far more chaotic. Could this be evidence of a rare early fluctuation that prevented matter from clustering together in the region? Some astronomers suggest that this vast emptiness formed when the universe was just beginning to evolve, a piece of space that simply never filled with galaxies like other parts of the cosmos. While most voids are connected to the large-scale structure of the universe, Bootes breaks away from this network. It lies separate from many of the known filaments that stretch between galaxy clusters. What's more, the few galaxies that do exist within the void seem to be behaving differently than what is typically observed. Their isolation means that the standard gravitational influences they would experience from neighboring galaxies aren't present, creating a situation where they don't follow the usual cosmic expansion patterns. Instead, they seem to be drawn together in strange ways, leading scientists to believe that dark matter could be at play here in unique ways. Dark matter, the invisible substance that makes up a significant portion of the universe's mass, is suspected to exist throughout the cosmos, even in voids. In Boots, though, dark matter may be the only thing holding the few existing galaxies in place. Without it, these galaxies could drift away, making the void even larger. But how can dark matter, which we can't directly observe, have such a profound influence here? That's a mystery researchers are still trying to unravel. The idea that such a massive expanse could contain nothing but invisible dark matter brings a deeper level of eeriness to the Bootes void. In terms of dark energy, the force responsible for accelerating the expansion of the universe, Bootes serves as an ideal location for study. Because there is so little visible matter, the effects of dark energy are far more pronounced here. The lack of galactic clutter means researchers can observe how dark energy behaves in a region largely free of gravitational interference. It could be that Bootes is expanding at a faster rate than the rest of the universe due to the unopposed effects of dark energy. If this turns out to be the case, it might be a crucial clue in understanding how dark energy will eventually shape the fate of the cosmos. But why is there so little matter in this region? If Bootes truly was shaped by early fluctuations in the universe's density, then it's possible that this part of space never had a chance to form galaxies at all. It was born empty, and it stayed that way. However, this raises another question. Could even larger voids exist that we've yet to discover? If Bootes is one of the largest cosmic voids we've observed, what's to say there aren't even larger ones lurking in the distant reaches of the universe, beyond the range of our current instruments? Some crazy theories say that the Bootes void could be a way to get from one part of the world to another, or even to a different realm. Although not universally agreed upon, this idea does lend mystery to the vacuum. Areas of space this large might theoretically host quantum tunneling, a phenomenon in which two or more universes momentarily collide. If that were so, Bootes might not be merely empty space, but rather an essential part in deciphering the very essence of reality. There are also strange rare events occurring within the void despite its emptiness. The galaxies that do exist here are merging at rates not seen elsewhere. Typically, galaxy mergers are influenced by their proximity to other galaxies, but in Bootes, these mergers happen in extreme isolation. This makes each collision a unique event, free from external interference. These galaxy mergers offer scientists a rare look at how galaxies interact in near-perfect isolation, giving us insights into the evolution of galaxies in extreme environments. The possibility that extraterrestrial races have found a safe haven in the Bootes void is another theory. Because of its relative lack of human activity, it would be a perfect hiding place for a highly developed civilization. It would be more difficult for outsiders to discover signals or technology traces in such a huge and deserted area. Though completely conjectural, it begs the question, may the Bootes void be concealing something unknown to us? If this is the case, what does it mean for the likelihood of life on other planets? Standing in its center, surrounded by nothingness, would be like experiencing the ultimate isolation in the universe. The vast distances between the few existing galaxies would make travel or communication almost impossible. If you were in the middle of the Bootes void, it would feel like being cut off from the rest of the universe, an infinite, cold, and empty expanse stretching out in all directions. Could such a place represent the future of the universe? As dark energy continues to push galaxies farther apart, voids like Bootes may become more common. Eventually, billions of years from now, the universe could be filled with these massive empty spaces, with galaxies scattered so far apart that they no longer interact. The Bootes void might be a glimpse into the universe's far future, with its eerie lack of matter and mysterious behavior, standing as a silent testament to the strange, unpredictable forces that govern our universe. Whether it's an ancient remnant from the early cosmos, a region dominated by dark matter, or even a hidden gateway to another dimension. The Great Silence. Why haven't we heard from aliens yet? With a galaxy filled with trillions of stars and potentially even more planets, the silence from the cosmos raises a crucial question: where are all the aliens? This enigma, often referred to as the Fermi paradox, points to the unsettling contradiction between the high probability of extraterrestrial life and the total absence of any evidence for it. The question of why we haven't heard from alien civilizations despite the vastness of the universe has given rise to many theories, each more fascinating than the last. One possibility lies in the zoo hypothesis, an idea that portrays humans as animals in a galactic zoo. Imagine being in a zoo where the animals know they're being watched, but can't interact with their observers. Could it be that advanced alien civilizations are watching us, but purposely avoiding contact? They might be silently observing us from a distance, allowing humanity to evolve on its own without interference. This non-intervention could stem from the belief that humans are not yet ready to integrate into a larger, more advanced cosmic community. Much like we watch wildlife without disturbing their habitats, extraterrestrial civilizations could be treating Earth with similar caution. Our isolation might be intentional, meant to protect the natural evolution of our species. While the zoo hypothesis offers a peaceful scenario, the dark forest theory paints a much darker picture. In a forest at night, the last thing you'd want to do is make noise and attract predators. This theory suggests that civilizations stay silent out of fear. If the universe is a dark forest, then every civilization is like a hunter, staying quiet to avoid attracting attention from potentially hostile beings. In this cosmic survival game, broadcasting one's presence could be a death sentence. Rather than trying to make contact, alien civilizations may be deliberately hiding from one another, ensuring their survival by keeping their existence secret. This silence, then, isn't due to a lack of life, but because life is too afraid to reach out. Could it be that Earth is one of the few habitable places in the entire universe? The rare Earth hypothesis proposes that while microbial life may be common, complex and intelligent life might be extremely rare. Despite the vastness of the universe, life as we know it may require such a precise set of conditions, perfect distance from a star, specific chemical compositions, and the presence of water, that Earth could be one of the few planets to have ever met these criteria. This theory challenges earlier assumptions that life must be everywhere in the universe simply because it happened on Earth. Instead, it could be that Earth is a cosmic anomaly, making the silence not an absence of civilizations, but a consequence of their rarity. But maybe the problem isn't the existence of life, it's the technological inequivalence. Different civilizations may exist at vastly different stages of technological development. Some might be their equivalent of the Stone Age, while others could have surpassed us so completely that their methods of communication are far beyond our understanding. It's possible that alien civilizations aren't using radio waves or other technologies we're familiar with, meaning we could be listening for the wrong signals entirely. The idea that we're stuck in a technological mismatch with alien civilizations offers a more optimistic explanation for the Great Silence. They could be out there, but we simply don't know how to hear them. Another thought-provoking idea is the cosmic quarantine hypothesis, which suggests that Earth is deliberately kept in isolation from other civilizations. Much like how we quarantine areas to prevent contamination, the galaxy could be under the control of an advanced species that enforces a no-contact rule for planets like ours. We might not yet be evolved or technologically advanced enough to join a greater galactic society. In this scenario, aliens could be aware of Earth's existence, but have agreed to not interfere, allowing humanity to develop on its own terms. The silence, then, is enforced by a galactic quarantine that isolates us until we're ready for first contact. The idea that we're listening at the wrong time also challenges our understanding of the universe. Civilizations, much like stars, have life cycles. They rise, flourish, and eventually fade away. If an advanced alien society existed millions of years ago but collapsed before humanity developed, we might be searching in vain for a civilization that no longer exists. Alternatively, there could be civilizations that have yet to reach the level of advancement needed for interstellar communication. Time could be the key factor here. Our search for alien life may simply be out of sync with the timeline of other civilizations, leaving us stranded in a cosmic void of silence. With the self-destruction hypothesis, there is now another scary option for the Great Silence. Is it possible that intelligent life is fundamentally damaging to itself? It is possible that every technologically sophisticated society will inevitably create the tools that bring about their own downfall, whether it be nuclear weapons, environmental destruction, or artificial intelligence. The cosmos would be a horrific wasteland if civilizations routinely destroyed themselves before reaching out to other worlds or exploring their own galaxy. Our lack of contact with alien civilizations may be due to this sad trend. Ours doesn't live nearly long enough. But suppose we have previously received signals from extraterrestrial civilizations, and we have just misunderstood them. It is possible that humans have previously detected extraterrestrial transmissions, but we have mistook them for celestial events, according to the misinterpretation of alien transmissions idea. In principle, odd astronomical phenomena like pulsars and quasars may be messages from faraway civilizations because of the regular, repeating signals they broadcast. Perhaps the extraterrestrial communication we have been seeking is actually included inside the cosmic noise that we have been referring to. Perhaps our limited grasp of extraterrestrial communication is to blame for the seeming lack of sound. We may not have been the first hosts for life on Earth, according to the intriguing panspermia hypothesis. Alternatively, it may have originated from another galaxy and been seeded there. Extraterrestrial life may already be residing in our bodies if life can propagate through space rocks like asteroids and comets. The extraterrestrials we're looking for may be our own forefathers in this case. Maybe we shouldn't wait for a communication from space to figure out how we're all connected in the universe. Maybe we might investigate where life on Earth began. The Great Silence could be more than just that, a reflection of the universal origins of life. In the end, signal degradation over time gives a clearer reason for the silence. Even the quickest transmissions, such as radio waves, can take hundreds, if not millions, of years to travel between galaxies and stars because of the enormous distances separating them. It is possible for signals to deteriorate over such long periods of time, becoming undetectable due to their weakness or distortion before they reach our ears. Interstellar gas, dust, and magnetic fields are cosmic phenomena that might further distort or obfuscate these signals, rendering them incomprehensible as anything other than random noise. It is possible that any transmissions sent by extraterrestrial civilizations are too weak for our senses to detect. The Great Attractor, the cosmic lure, pulling us toward oblivion. The Great Attractor is a strange event in space that draws whole galaxies toward it with its unseen mass. This mysterious force's precise position is unknown since it is concealed by the Milky Way's zone of avoidance. What is known, however, is that it is not a single thing. Rather, it stands for a densely populated area filled with dark matter, the existence of which can only be inferred from gravitational effects, rather than observed directly. Understanding the dynamics of the Great Attractor starts with the unusual flow of galaxies in our local group. Galaxies are not simply drifting apart due to the universe's expansion. They are also accelerating towards the Great Attractor at a staggering speed of about 600 kilometers per second. This unexpected movement challenges our assumptions about how galaxies interact on a grand scale. The location of the Great Attractor is still a mystery, even as scientists are learning more about its features. Because of its location behind the massive disk of the Milky Way, astronomers have had a difficult time determining its precise coordinates. Because of the cloud cover, scientists are still trying to figure out what this cosmic force is. The Norma cluster and the Hydra Centaurus supercluster are two adjacent galaxy clusters that are affected by its enormous gravitational grip. Crucial to their development and creation is this gravitational contact. Scientists are rethinking their theories of cosmic dynamics in light of the Great Attractor's impact, which emphasizes the interdependence of cosmic structures on a huge scale. Dark energy is crucial to comprehending the Great Attractor. Curiously, the Great Attractor's gravitational pull and the presence of this enigmatic energy, which is believed to be driving the universe's rapid expansion, cross paths. The intricate nature of cosmic expansion in relation to gravitational pull is a mystery that scientists are striving to understand by investigating the interplay between these two forces. Observations of the cosmic microwave background, CMB radiation, reveal intriguing anomalies that may be connected to the Great Attractor. These anomalies suggest that a larger cosmic structure could be influencing the uniformity of the CMB, offering tantalizing clues about the history of our universe. As light from distant galaxies passes near the Great Attractor, it bends, creating distorted images that provide indirect evidence of the mass distribution within this mysterious region. This lensing phenomenon not only helps astronomers infer the Great Attractor's properties, but also deepens our understanding of how gravity operates on a cosmic scale. Some researchers propose that it is not a singular entity exerting gravitational pull, but rather a complex web of multiple structures, including superclusters and voids. This idea challenges traditional notions of gravitational attraction and encourages a more nuanced view of how large-scale structures influence the cosmos. They are also pondering the implications of the Great Attractor for the future of the universe. If this gravitational influence persists, it may result in a collision course for our galaxy and others in its vicinity. This raises questions about the long-term fate of galaxies drawn toward this cosmic entity and the potential for catastrophic interactions. Looking ahead, advancements in observational technology promise to shed new light on the Great Attractor. Upcoming space missions, such as the James Webb Space Telescope, are poised to provide insights into its properties and the gravitational effects it exerts on surrounding galaxies. These advancements may lead to breakthroughs that redefine our understanding of this mysterious force. The pursuit of knowledge about the Great Attractor is fueled by curiosity about what lies beyond. As researchers continue to uncover its secrets, they wonder if there are even larger structures lurking in the cosmic void, pulling galaxies in different directions. The exploration of these forces offers an opportunity to reshape our view of the universe and its intricate dynamics. While the Great Attractor remains a subject of fascination and intrigue, its impact on cosmic evolution is undeniable. The gravitational forces at play within this region serve as a reminder of the universe's complexity and the interconnectedness of all things. As we unravel the mysteries of the Great Attractor, we gain insight into the cosmic forces that shape our existence and the destiny of galaxies. In this cosmic narrative, the Great Attractor serves as a poignant reminder that our universe is an ever-evolving entity, influenced by forces beyond our immediate understanding. The journey to comprehend its nature and implications leads us deeper into the fabric of reality, encouraging us to question our perceptions of isolation and unity. Blazars, cosmic jets from hell. Blazars are a type of galaxy, but unlike ordinary galaxies, they have an active core dominated by a supermassive black hole. These cosmic monsters are among the most violent phenomena in the universe, launching massive plasma jets at nearly the speed of light. Unlike other active galaxies, blazars are terrifying because their jets point directly toward Earth, sending radiation our way in staggering amounts. The plasma jets emitted from blazars are more than just a spectacular display of power. They are a glimpse into the heart of a supermassive black hole in action. These jets are made up of highly energetic particles, protons, electrons, and sometimes heavier ions, hurtling across space. The energy behind this launch is gravitational, derived from the surrounding material that gets trapped in the black hole's orbit. The speed at which these particles travel is close to the speed of light, a boundary that's rarely crossed by anything with mass in the universe. These plasma jets span distances so vast that they can reach thousands of light years from the black hole. The sheer energy required to launch matter at this speed is a testament to the unimaginable power of blazars, and it leaves us with a daunting question. What could happen if these jets were aimed at a planet? Defining traits of blazars is that their jets are pointed directly at Earth. This is no coincidence, but rather a chilling fact of their alignment with us. Blazars are only categorized as such when viewed from this specific angle, making us the target of their jets. In another part of the universe, blazars might appear less threatening, but from our vantage point, we are witnessing the raw energy of these jets head-on. This means that despite the distance between us and the blazars, we are exposed to far more of their radiation than if the jet were pointed away. The feeling of being in the direct line of fire of one of the most powerful cosmic forces is enough to make anyone stop and think. What drives a blazar is the feeding of a supermassive black hole. These black holes, millions or even billions of times the mass of our Sun, lie at the core of galaxies. When material gets too close to one of these cosmic giants, it gets sucked in, but not all of it disappears. The intense gravitational pull heats up the material, causing it to release energy in the form of radiation. The rest gets flung outward in the form of plasma jets. Blazars are the ultimate expression of this destructive feeding process. The environment near a supermassive black hole is nothing short of chaotic. The temperatures near the event horizon can reach billions of degrees. Matter that once made up stars, planets, and cosmic dust gets shredded apart and transformed into high-energy particles. As this material orbits the black hole, it gains more and more speed, spiraling inward until it either gets sucked in or blasted out in a jet. The closer the matter gets, the faster it moves, and the more energy it releases. Blazars give us a rare glimpse into the fury that lies near a black hole's event horizon, the point beyond which nothing, not even light, can escape. Though they constantly emit radiation and particles, they can experience sudden bursts of activity known as gamma-ray flares. These outbursts are so powerful that they can cause the blazar's energy output to increase 100-fold in a matter of hours. These gamma rays are the most dangerous form of radiation, capable of sterilizing entire planets. If a flare from a nearby blazar were to hit Earth, it could strip away our atmosphere, leaving the planet vulnerable to cosmic radiation. These gamma-ray flares are rare, but they are real. In 2015, scientists detected a blazar that suddenly brightened by a factor of 100. The sudden spike in energy, which lasted for days, was traced back to a flare of gamma rays. If Earth had been in the path of this flare, the consequences would have been catastrophic. Even though the blazar was millions of light years away, the radiation was strong enough to be detected on Earth. The prospect of such an event occurring closer to home is enough to keep astrophysicists up at night. The jets emitted by blazars are not just light shows. They also carry with them cosmic rays, particles that bombard Earth from all directions. Cosmic rays are one of the most energetic forms of radiation in the universe, and their source has long been a mystery. Scientists now believe that blazars are one of the primary producers of these particles. These cosmic rays travel vast distances through space, and when they reach Earth, they collide with our atmosphere, creating showers of secondary particles. While most of these cosmic rays are harmless, their sheer energy is a reminder of the destructive power of blazars. Despite their unimaginable power, blazars make no sound. They exist in the vacuum of space, where sound cannot travel. All of the chaos, the destruction, the high-energy collisions, it all happens in complete silence. The idea that such violent forces can exist without a sound is eerily unsettling. It is a reminder that space is not only hostile, but it is indifferent to the life that exists within it. What makes blazars even more horrifying is their potential to quench star formation. When a blazar's jet passes through a galaxy, it can heat up the surrounding gas to such an extent that it prevents new stars from forming. This process, known as feedback, effectively kills the galaxy, stopping it from producing new solar systems. Blazars, therefore, can be thought of as cosmic executioners, not only causing destruction in their immediate surroundings, but also ending the life cycle of entire galaxies. While blazars are terrifying in their own right, they also represent a shadow of the early universe's power. Many of the blazars we observe today are billions of light years away, meaning we are seeing them as they were billions of years ago. These ancient cosmic engines were formed in the early stages of the universe, when galaxies were colliding more frequently and supermassive black holes were more active. Observing blazars gives us a window into the chaotic conditions that shaped the universe as we know it today. Blazars are also thought to be responsible for some of the most energetic particles in the universe, cosmic rays. These high-energy particles travel through space at nearly the speed of light, and when they collide with our atmosphere, they create showers of secondary particles that can affect everything from the electronics in satellites to life on Earth. While our atmosphere protects us from most of the harmful effects, the fact that these particles come from billions of light years away is a reminder of just how far-reaching the influence of blazars can be. The potential for a blazar-induced extinction event, while remote, is not entirely out of the realm of possibility. A gamma-ray burst from a nearby blazar could strip away the Earth's atmosphere, leaving the planet vulnerable to the harsh radiation of space. While this is an extremely unlikely scenario, it is a reminder that the universe is not a safe place. The forces at play in blazars are so powerful that they could wipe out life on Earth in the blink of an eye, leaving nothing but a barren, irradiated planet in their wake. As we peer deeper into the cosmos, it becomes clearer that the universe is a place of profound mysteries and unimaginable dangers. From cosmic entities that rip apart the fabric of space-time to jets of plasma speeding toward Earth at incomprehensible speeds, it's as if the universe itself is teetering on the brink of chaos. Yet in all this terror, one question remains unanswered. Why haven't we encountered other forms of life? Could it be that the same forces which seem poised to obliterate everything also keep us isolated? In the face of the horrifying phenomena we've explored, from blazars to black holes, we are left with a sobering realization. Maybe we are not meant to find others. Or worse, maybe they are already gone. The universe may not just be silent. It could be a graveyard, and we're the only ones left to hear its eerie echoes. I hope you enjoyed the video. Feel free to subscribe if you did. Thanks for watching.